Hello everyone. Today I will be starting with the topic Combinational Circuit, which is a part of a digital logic design subject. I am Ritulika Ghosh Dastida, Assistant Professor from Babu Banasi Das University, Lucknow. So let's start. What are actually combinational logic circuits? So combinational logic circuits are basically a connection of different logic gates which are used to produce a specific output for certain specified combinations of input variables. Over here, whatever the output is, it is only dependent on the present input and there is no storage involved or there is no feedback requirement in this combination logic circuit. So this shows the block diagram of a combination logic circuits. Here we have n input variables and we have n input variables and we have m output variables. So these outputs are dependent on these present input variables. There is no requirement of any feedback in this combination logic circuits. What are the importance of combination logic circuits? So these are used in your digital electronic devices such as computers, where we require to perform some operations on data. For example, your half adder or full adder, which are used for taking the addition or arithmetic addition of your two binary digits, and then we get sum and carry as your outputs. So there are some important features of your combination logic circuits. These are at any particular instant of time, the output only depends on your present input, which we have also seen in the previous slide of your block diagrams. So there are n inputs and n outputs. There is no require of memory as there is no storage over here. The working speed of this circuit is fast because there is no feedback over here. Due to the absence of feedback, the circuit designing is also not very complex, and it is also time independent circuit because it only depends on the present values of your input. So the applications of combination circuits are your digital calculators, computers, digital signal processing, robotics, and they're also used in digital communication. So we will proceed with the first combination logic circuit of our syllabus, that is your half adder. So this slide shows you the block diagram of a half adder. You can see this is the block diagram over here. So A and B are the two binary inputs and the outputs are sum and carry. So let's see over here the combinations of A, B is 0, 0, 0, 1, 1, 0 and 1, 1. Okay. So let's perform the arithmetic operation over here. 0, 0 sum is 0 and there is no carry bit, so carry is 0. Again over here 0, 1 is the sum is 1 and your carry is again 0. For 1, 0 the sum is 1, 1 plus 0 is 1 and carry is 0. For 1, 1 the output is 1, 0, so the sum is 0 and you have a carry bit over here, that is a 1. Now we will draw the K map using the truth table. So the K map over here shows your two variables A and B, and now we can see, so wherever the sum is high, which is 1 and 2, we will put it over here. So we see the expression is your A B bar plus A bar B, which is nothing but your A XOR B, and for carry you have A dot B. Now using this K map, we will draw this circuit diagram. So we have A and B as two inputs, and then we take this XOR gate over here and we get sum A bar B plus A B bar, and we use this AND gate and we get this C is equals to A dot B. So next is a full adder. Full adder is you are having three inputs A, B and C in. So half adder was here for 2 bits, this is for your 3 bits. Again the outputs are sum and carry. So let's see the truth table over here. Again you have 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 1 1 0 and 1 1 1. Now we will start addition over here. So first we will add these two bits. So 0 plus 0 is a 0. With that 0 we will add this. So the sum is 0 plus 0 is 0 and no carry. So carry is 0. We will see over here 0 plus 0 is 0 plus 0 is 0 and that 0 plus 1 is a 1 and again carry is nothing. Carry is 0. Let's start. 0 plus 1 is 1 and that 1 plus 0 is a 1. So again carry bit is 0. 0 plus 1 is a 1. That 1 plus 1 is a 1 0. So your sum is 0 and your carry is 1. Okay. Let's start it again. 1 plus 0 is 1. 1 plus 0 is 1. So you have sum is 1 and carry as 0. Again 1 plus 0 is 1 0 and you have 1 plus 1 is 1 0. So sum is 1 0 and carry is 1. Okay. Anyways, 1 plus 1 will give you 1 0. 0 plus 0 will give you 0. So sum is 0 and carry is 1. 1 plus 1 will give you 1 0. 0 plus 1 will give you 1. So your sum is also 1 and carry is also 1. Now using this truth table, we will draft the KMAP again for carry and for sum. So we will mark the values and we will find the expression. So carry expression is AB plus ACin plus BCin and sum expression is this, which is nothing but again A XOR B XOR Cin. So let's see the circuit diagram. So for sum we have A and B passed through the XOR gate. So this will give us A XOR B over here, and again this Cin is coming as an input to this second XOR gate. So this will give you A XOR B and XOR Cin. So we get a sum. Now again similarly by using this expression we are using the logic gate and we get this carry out. And this is the circuit which is shown, full adder circuit using two half adder circuits. So first half adder is used, the output of the first half adder along with the third pin input is given to the second half adder and we get the just see this we are getting A XOR B with the first half adder and then this Cin is given over here the second half adder and we get the sum over here which is the 3 input XOR which is A XOR B XOR Cin. Similarly we get the C out over here. Next circuit that we are going to study is a half subtractor. Half subtractor is again 2-bit binary subtraction. So this is 0 and 0. 0 minus 0 is 0 and 1 is also 0. Similarly 0 minus 1 is 0. We will take a board over here. So this will become 1 and 0 minus 1 which is 1 and borrow is 1. Similarly over here 1 minus 0 is your 1. So the difference is 1 and your borrow is 0. Again 1 minus 1 is your 0 and binary borrow is also 0. This shows the block diagram and then using the truth table we will mark for the KMAP, so for difference and for borrow we got this schema, we find the expressions over here, and then we draw this multi-circuit diagram. Similarly, for closed-loop tracker, again it is same A, B, and borrow in, and then we have a difference, and we have hold out. Okay. Now over here again 3 input 0, 0, 0. So 0 minus 0 is 0, and again 0 minus 0 is 0. So both difference and borrow is 0, 0. Similarly, 0 minus 0 is 0, and 0 minus 1, you will take a borrow, so borrow that is 1, and the difference will be 1. Okay, so this way we will complete this table, and then we will get this K map, and using the K map, we get the expressions of A, B bar, A XOR B in, and we get the expression for B out of A bar B plus A bar B in plus B in. Using these expressions, we will draw this circuit diagram. Again, this is a circuit diagram of a full subtractor using two half subtractors. So again, see, this is the first half subtractor with having two input. So this will give you an A XOR B over here, and this B in is coming as an input over here through this XOR gate, and you get a difference of all the 3 bits, that is A XOR B XOR B. Similarly, we will get the B out. Thank you for today. That's all for today. Now, there are many more circuits such as multiplexer, decoder, encoder. These are also a part of your combination circuits. So that's all for today.